But when this model is deployed to some business scenarios and generates revenue, this entity that own this model and the computation resources would not give this revenue or profit back to the contributor of the data. So this generates some fairness issues of in the centralized AI. So yeah.
Hi, everyone. I'm Shane. I'm a research partner at Hack VC, and I'm joined today by Ming, who is at Zero G. So, Ming, do you want to introduce yourself?
Yeah, thanks, Shen. I'm Ming, and I'm the co-founder and the CTO of Zero G. And my background is on the technical side. Now, before joining the Web3, I was working in the Microsoft research for 11 years, and my major area is on the distributed system and also the large-scale AI and machine learning platform. And in 2018, I actually quit from Microsoft, and I co-founded another blockchain project called Conflux with Fan Long, who is also one of the co-founder of Zero G. And in the Conflux, I actually working with a team to build a highly efficient layer one blockchain, which inherit the Nakamoto consensus, but introduced with a novel consensus protocol that can secure out better, and we can achieve about 3 to 6,000 TPS without sacrificing the decentralization and the security. And in that project, I accumulate a lot of experience on building the blockchain infrastructure. And then in 2 years ago, and both Fan and I were connected with Michael, who is our CEO, through Thomas, another co-founder of Zero G. And we actually discussed to building something new, and we're brainstorming, and we think that it is very exciting to bring the blockchain to the AI area, so that we can either using the decentralized technology to help AI to improve its to overcome its drawback in the centralized environment, and also we can using the AI technologies to make to bring better user experience of the blockchain, so that we can really make the blockchain have value in the traditional business and the industry, so that we can give the mass adoption of blockchain. And so that's why we are here at Zero Gravity. And so in Zero G, actually we are trying to build a we call it the largest layer one for AI, and with another phrase that I think we are also building a decentralized AI operating system, so that we are building a platform for the AI applications to manage the decentralized hardware resources like the storage and the computation, so that we can easily onboard any AI workload in the Web 2 area to the Web 3, so that we can make the AI really decentralized and transparent and democratized. Yeah.
Yeah. So maybe do you want to get into what you mean by AI and then just the basic centralized version of it? I'm assuming you're mainly talking about LLMs.
Yes. So
training and then inference, basically.
yes, of course. So so when I talk about AI, I think it's the general AI. So basically, LM is one of the important category of the AI area, and but we can also do the other models like the vision and the audio kind of stuff. And So AI, I think it's just the recent technology of AI is mainly based on the deep neural network, which actually is borrow the human neural structure to organize um, the functions in the neural way, and they have them connection, and we can have the feed forward phase to give by generating the output from the input signals, and it used this back propagation to transfer back the gradients to update the weights based on the object function and optimization mechanism. So ideally, with the consistent running by processing a huge amount of data, and it makes this model can build in a function that can generate the output with the given data to make the output really close to the labeled. So basically, the deep neural network looks like this, and it has multiple layers of the neuron, and the neuron can be connected with the edges, and the input data be digitalized, and usually represented as some vectors, and this data can be audio, video, and also the text, and this so this neural actually just abstract the data in the linear function, and for example, on each edge there's a weight, the different weight actually it makes this function like a y equals x times weight, and of course x is the vector, for example, and then this process can be iteratively applied on different layers, and at output it generates so yeah, in the centralized way, actually the model is controlled by the some entities or some individual, and the data and also processed by the entity. So, and also because this neural network has a objective function, which also abstract as a loss function. So the goal of the AI is to minimize the loss. So in that sense, what the model can really do really depends on what's the target function or what's the loss function. So if in the centralized AI, first of all, we don't know what is the loss function that it used. So the loss function actually, or the objective function actually directs the AI intentions. It actually can make the AI do good things or evil things, and also in the AI workload, we don't know what's data that the centralized entity used, and which means that the label can be intentionally manipulated. For example, if the input data is a picture of dog, and it can label it with a cat, and also it may change some not significant bits in this figure, which means that there's a hidden signal that can trigger this wrong label output. So if the model is trained in this way, and when this model is applied to the user real life, um, there could be some attackers that knows the signal, how to trigger this model to generate the wrong prediction. So that could be that could be harmful to the user life that use this model. And so this is one evil behavior that that one issue that the centralized AI will have. And another problem is that usually this model is controlled by the entity, and it also needs to process a huge amount of data. But where the data comes from, and the data may comes from the all the internet data, right? All the internet, all the websites in the web pages in the internet. But the data actually is not are not contributed by this entity. So the value of the model has a large part of the value of the model comes from the data. But when this model is deployed to some business scenarios and generates revenue, this entity that own this model and the computation resources would not give this revenue or profit back to the contributor of the data. So this generates some fairness issues of in the centralized AI. So yeah.
So there's kind of like a hybrid, right? Because there's centralized AI systems like OpenAI and Anthropic, which don't release their model weights, the data they use to train or anything. But there's also Hugging Face, which releases a lot of open source models, right? So that's kind of like in between you and them, right?
Yes. Certainly the open source model make some improvement to on addressing these issues, but not entirely solve this problem. So at least when you open source the model, and there are a lot of users can use this model with their input data, and they can evaluate what's the behavior of this model, and so that can judge whether this model is good or not. And but because we still don't know how the model is trained from, and there's still some hidden information there, and there's still some possibility that some evil things can happen there. So we are trying to using the decentralized technology to make the AI training and inference process totally transparent, so that we can control whether it is aligned to the human intention and the value.
So like your kind of number one goal is transparency in a sense.
Yes.
Okay. So yeah, do you want to get into zero gravity and your design?
Sure. So in zero G, actually, we are treating us as a decentralized AI operating system, which means that we manage the all the decentralized hardware resources for the AI workload. What does that mean? So first of all, any decentralized technologies will have its core piece, that is blockchain. So zero G has its own blockchain. This is the layer one. Don't like that. And on top of the layer one, and we build some separate component, some separate systems. That is, one is the storage. and the other is the compute network.
So the L1 blockchain is just some sort of like Turing complete VM blockchain where you can send funds and create smart contracts.
Yes. It is EVM compatible, and we also have some scalable design of it, which I can describe later on.
Mm-hmm. That's okay.
Yeah. So, and on top of that, and we built a element layer. Element node layer, where we will apply a bunch of element node whose responsibility is to checking the health status in the entire network, and also check whether the model trained from the system are aligned with the human intention and value. Yeah, this is the highly architecture of that, and so this is the underlying piece, and on top of that, and we provide a series of SDK and interface for the applications to onboard on this decentralized. Onboard this decentralized AI operating system. Yeah.
So the L1 blockchain is kind of orchestrating the storage and compute in a sense.
Yes.
So yeah, what kind of part of this should we talk about first?
I want to first talk about the storage network.
Okay.
Yeah, can we? Assume this is our blockchain, and then we have a separate system that consists of a bunch of storage nodes, for example. So each node is a computer with large enough storage capacity, and the node also connected with a gossip network or P2P network. And yeah, so each storage node server is in charge of store the user uploaded data. So user can send data to the storage node, and at the same time, a user can construct a signature of the data.
Like let's take an example, like they want to upload open web texts or something.
Yeah, web text. Yeah. Yes. Send the signature of the data to the smart contract on the chain, and so then what we have is that user can send a series of this data in the system. So in smart contract, it maintains the sequence of the signature of the data. But the real data will be put into the storage node separately. And so in that sense, all this storage node will store a lot of user data there. When users submit the signature to the smart contract, it also pays a fee correspondingly. The fee can be decided based on the size of data and how long he needs the data can be preserved. Yeah, so it's fees. The fee, of course, can be the 0G token. And this fee will eventually be used as an incentive reward to the storage node who really store this data. So when we have this sequence of the signature, and the system will periodically generate some random samples in the historical position and ask the storage node to submit the proof of the accessibility of that piece of data. So every storage node will try to generate the proof and submit to the smart contract for verification. Proof of.
When you say sequence of signatures, is that because, if you have a big data set, you chunk it up into a bunch of small parts?
The signature, usually signature is small. So the signature can be stored on the smart contract.
Well, yeah, but if you have 40 gigs of data, you're saying you chunk it up into a bunch of small parts and then take signatures of each chunk?
Oh, yes. Yes, that's okay. So any file, the data actually, any file can have a signature. The file can be very large, and I think we take the data as a file granularity. So every file has a signature. That's the case, and currently we don't chunk the sequence of the signature further. Yeah, but certainly if the signature itself is large enough, and we can certainly using other maybe the hierarchical design of that. But yeah, later on I will also talk about how we can scale out the blockchain so that can kind of solve this problem.
Is there any redundancy in the storage?
Yes, there is. So because if we want to store the data in the storage in a reliable way, there should be some redundancy there. So currently we adopt this I would say the replication. So every data get into the storage node can be will be propagated to other storage nodes, so that the data can be duplicated. But because for example this call it file 1, and this is the file 1, and the data can be replicated to other node. Yeah, because the node will submit the proof of access to get the mining reward, and the mining reward is the fee user paid for this data, and which means that if there are multiple nodes store the save the same data, they actually share the fees from the user.
Mm-hmm.
Yeah, so which means that if we have more storage node save the same data, each storage node will get less reward. So so this will naturally get into a balance that the reward will be matched to its cost, right? So that means that in our system we have a reasonable pricing for each file, each data, and but the users can double or triple put more fees for the data, so that more storage nodes will love to store this data because it is profitable, right? And so that the more user pays for the data, the more replicas exist in this network, and the more reliable the data will be. That's basically the design. And yeah, so this actually I think solve the reliable storage of the data, but consider the scalability issue. So because users will submit a lot of data, and so if all the data will be replicated to other nodes, where the scalability comes from, right? So in that sense, we actually also design a sharding mechanism to make the storage network have the horizontal scalability. And yeah, so our sharding mechanism works like this way. Let's put this sequence larger. So because it is a decentralized system, there's no mechanism that can force a storage node to stick to some specific shard, right? And so we allow the storage node to self-defining the how they want to store the how many shard in the system and which shard that the storage want to save. The only thing that to fix is the scheme of the sharding. So in our system, we shard the data in a round-robin way along the data sequence. For example, if we have two shards, and we can have the position 1 as shard 1 and the position 2 as shard 2, and yeah, and so on. So in this case, when the user upload this data to the system, it can put one shard data to one server and another shard of data to another server, so that this data upload can be executed in parallel. So so that the upload performance can scale out linearly, and of course, more shard will lead to higher scalability, higher data upload throughput, and we have done some experiment on testing the scalability, the throughput of the data uploading, and we actually use a 32 shard to achieve 32 shard to achieve 2 gigabytes per second data throughput, which is as far as we know, that it is the largest data throughput for any existing decentralized storage system. Yeah.
Cool. So, and obviously the main use case here is for storing AI data sets, so supervised data sets.
Yeah, so this is this is basically the storage network, how storage network works. Yeah.
Awesome. So should we talk next about the compute network?
I would like to first get into the blockchain, how we can scale out the blockchain. Okay.
Sounds good.
So, based on the previous description, although we only upload we only send the signature of the data onto the blockchain, but if the data scale is super large, and eventually the blockchain will become the bottleneck, because the blockchain is not it's a monolithic system, and it is a fully replicated system. So there's no scalability there. But the storage network has the horizontal scalability. It can scale out based on the sharding. So to avoid the blockchain becomes the bottleneck, we actually also trying to employ the sharding mechanism to the blockchain, our 0G blockchain. But unlike the traditional way of building a sharded blockchain, so usually, uh, how to say, in the blockchain system, we have a bunch of validators, and these validators will get to reach some consensus on the state change, right? And so any data will be broadcast in this entire network. But if we want to shard, and a existing alternative way is to how to say split the validators into the shard. For example, we can make a subset of the validators in the shard 1 and another subset of validators in the shard 2. The issue of this sharding mechanism is that so usually the security level of a blockchain really depends on the skill of the node and also the skill of node if it is based on the POW mechanism, also or the capital staked in the system, which is if it is a POS-based protocol. So let's consider the POS-based protocol. So because the shard has only a subset of the validator, so the capital is also much less than the entire network. So the shard has much less security level compared to the entire validator set. So that's what we don't want. And so we take another sharding mechanism. So assume we already have a blockchain that is already decentralized enough. And if we want to scale out the system, and instead of make the shard in a subset of validator, we actually want to use another way that we can build another. We can use some extra compute resources to construct another blockchain, but we want these two blockchains share the same staking status so that it behaves as in a single chain. For example, that means that these two chains will share the same set of validators. And each chain, the same validator will have the same voting power based on its stake. So in that case, the two chains will have the same level of security. And then we can treat each chain as a sharding of the entire system. But how we can do that? We need to find somewhere that we can put this staking status shared by the two chains. What we can do in the reality is that we can leverage another chain, another existing chain, and use that chain as a ledger to record the staking status of each 0G chain. What we can use is, for example, we can use Ethereum as a chain, because Ethereum has a very high level of security, so that we can very trust the state on the chain. And then we can also leverage some existing infrastructure built on Ethereum, like the restaking protocol. It could be the EigenLayer, and there's another called Symbiotics, also a restaking protocol. So currently, with 0G implementation, we actually leverage a Symbiotic. Let's see.
So the basic idea being like, since you're just basically storing like signatures and doing some checks on storage, you can get away with having a bunch of parallel kind of blockchains that share staking status because like the state between them doesn't really matter.
Oh, yes, yes. So yeah, so basically,
They don't share state. They have completely different state. I'm assuming.
yeah, we just no, no, we just want the two chains share the stake. So basically,
Not the state. They do not share state.
yeah, do not share state. Yeah, yeah, they just need to share the stake. Yeah, stake. So, for example, the zero G token can be bridged to the Ethereum and staked in symbiotic protocol. And then this stake information can be fetched by every validator in this chain, so that this validator can use this stake information to vote in the local consensus, in local POS consensus. Same here for the validator, same validator in the another chain, the other chain, it can fetch this status of the staking on the Ethereum, so that they can use this validator to do the to participate in the consensus in the other chain. And
So like one validator entity will run like a bunch of versions of the chain on different computers. Is that the idea?
yes, yes. So basically, so we can have the same validation side, and each validator can start and participate to multiple chains. And so the different chains will share the same set of validator, and we also want them to share the same staking status. So we use Ethereum as the place to store the staking status. So what we can do is that every validator can bridge zero G token to Ethereum to make it a ERC20 version and restake this zero G token on Ethereum to the restaking protocol, like Eigenlayer and say all symbiotics. And then each validator can fetch the staking status from Ethereum, so that the multiple chain will have the same staking status for the same validator. And in that sense, so every zero G chain will share the same level of security. And through this way, we can actually create arbitrary number of chains as long as the validator has enough local computation resources, right? So that we can scale out the chains with the entire zero G chains with a bunch of subchains. Ideally, this can scale out infinitely, and together with the storage network that I just described. And so then we have multiple subset of the storage servers that can connect to the different chains. So which means that we actually abstract multiple storage, logical storage for the AI workload, so that we assume that when zero G chain support a huge amount of AI workload or AI applications, and the different applications may use the different storage subnet to the connecting to the different zero G chain shard. And in that sense, the different AI workload can be independent with each other, so that they will not interfere, will not have frequent interactions among them. So in that sense, we actually can scale out the system very in an embarrassingly way. So this very like how our local computer, the desktop or PC, how the PC operating system manage the local hardware, local multi-core CPU for the applications. So the local CPU has multiple cores, and but the application when it runs in the operating system will schedule the applications to the different cores so that the different applications can run in parallel and yeah, without interfere with each other. So yeah, the same principles here, and also that's why we call our mechanism as a decentralized AI operating system, so that we can help the workload to manage the underlying resources. Yeah, so this is about the how we scale out the chain, and maybe next we get into the compute network.
Okay.
Is that okay?
Yeah.
So it is very similar to the storage network, and we also assume that we have existing blockchain there. Then we have, and then we also have this storage network, for example. And then we have a bunch of decentralized compute machines here. And each machine may provide enough computation resources, including the CPU and the GPU. And but it joins the network in a decentralized way, so that we don't know who provide these devices. But the user may have some query, want to use some services. So so any service actually it need to provide three things. One is the service type. So it can be the storage service, or the inference service, or even the model training services, right? And secondly, it need to have a quote for its service price, which means how expensive, what fees that user need to pay for each query of the services. And thirdly, and also the most important thing is the verifiability. So because we don't know who provide these computation resources, and if they claim that they will provide a model inference, for example, if it could be the Llama 3, for example, and if user give a query that they need to guarantee that this output really comes from the Llama 3 model, and so the service provider need to provide some proof that the output of the service really comes from the computation of the specified model. And the verifiability can be there could be multiple mechanisms to generate this proof. Someone could use the ZK-ML or OPML, optimistic one, or hardware-based like TEE. So in our system, we don't care about the verifiability mechanism. But in practice, we encourage users to use the TE-based solution because it is more cost-effective. ZK solution is too slow, and the OPML is not that secure. So we think the TE has reached the best trade-off. And so then our system, our compute network smart contract works as a middleman to connect the user payment with the service provider. So user first pay amount of fees. So when users select the specific service that they want to use, they actually prepay some money into a smart contract. And then users can interact with the service provider to submit a series of queries. And the service provider will accumulate a sequence of this request and response with the user signature and also the proof of the response result. And periodically, the service provider can submit the sequence of the request and the response sequence to the smart contract for settlement. Once the settlement got done, and the payment, the fee will be distributed to the service provider's wallet. And yeah, so this is how our smart contract, the compute network smart contract can coordinate the decentralized services to users. It's just like a decentralized Amazon that just like Amazon, in Amazon actually to connect the merchant with the users. But here we actually connected the computation of the service to the users to guarantee the trustworthy, to guarantee the secure payment and the service consumption. Okay, so yeah, and also because the users directly communicate with the services in the real computation, the system actually can easily scale out with more computing resources join the network. And the all the decentralized service providers behave behave like in the free market, so that if the service provider provide the same types of service and they have the ones with good, better quality and the cheaper price will have more users to use them. Yeah, so this is basically the compute network. And also the connection between the compute network and the storage network is that, for example, if this service is a inference service, it can actually store the model in the storage network. So when the service start serving, it first load the model from the storage to its local storage, so that it can provide efficient service for the users. Okay, so this is basically
So
how.
that's mainly for inference, right?
Yeah, no,
So
no, not
how about training?
yeah. Okay, so no, not only for inference. The service can also be the training service, which means that the users can also provide the data in its request to the service provider, and the service provider can run the training process based on that data. This is especially useful for the fine tuning, for example. For example, if we have already a foundation model from the storage network, it can be loaded into the fine tuning service, and the users, of course, users can do not need to submit the data directly to the server. It can also put the data into the storage network and allows and tells the service how to fetch the data from the storage network. So the data can also be uploaded from the downloaded from the storage network, and then the fine tuning the service can do this training locally, and after the training finished, and it can provide the user the result of the updated model, and this updated model can also be stored in the storage network, and then this service got done. This is for the single machine example, but this for the fine tuning and the training workload, it can even touch multiple servers. It needs to coordinate multiple servers to train the model because the data can be very large. So in that
Hmm.
sense, yeah, the users can it can work like this way. So one service can be a coordinator of the training service, and it can and the others can be the worker, for example, and worker W1, W2, W3, and this is a training coordinator, for example, and so the service can look like this, and um, the coordinator when it instructed the workers, it behaves as a user, and the workers as a service provider. So when the worker load the data partition and finish the training job, it will submit the result to the coordinator. Um, for example, like this way. And the coordinator can also verify the working results by using the verification mechanism of the worker, and the and then the user can interact with the coordinator. The coordinator also can run in the TE environment so that it can guarantee um, its a coordination logic. It's trustworthy, so that eventually the user gets um, the output of the training process from the multiple services. So this is about how they distributed training work in this compute network. Yeah.
Hmm. I mean, it's mainly useful for fine tuning because obviously training something from scratch this way is probably not a great idea.
Yeah, can also be used for the pre-training. We are actually current target to explore the possibility to do the pre-training in this decentralized environment. But of course, there could be some challenges because in the decentralized network, the network bandwidth is very constrained. So it generates a lot of cost during the training for the large language model, um, which will consume a huge amount of GPU resources. And the network bandwidth could become the significant bottleneck during the process. But we actually um, recently has done some research on overcome some kind of challenges and problems in this area by introduce some um, gradient compression uh, to minimize the communication costs across machines during this process. And also, we will apply some overlapping of the computation of the communication for the um, continuous, consequent, um, consecutive iterations so that we can minimize the computation cost. And we have already trained a model with 107 billion parameters. Um, yeah, that as far as we know, it is also the largest model that the people have trained in a decentralized environment. And yeah, we got some paper published to the public, and that's one of our research results recently. Um, yeah, so this is pretty the compute network, and
Mhm. And so, what was the final layer that was on top in your first picture? That was, you said,
alignment node, right?
alignment layer, okay, or alignment node.
So that kind of still ongoing and at very early stage. So basically, what we want to do is that um, since this model processing workflow in our system is kind of transparent, and we want to build how to say if we have compute and storage and chain, and we want to build a bunch of story element node, which could be lighter, and they can be some verifiers, for example. So for some training or inference tasks executed in the compute network, and the verifier can monitor result and can validate the model output for some inference tasks, and if they so it is itself can be a language model that can be that can have a small scale, so that it does not need to consume a lot of computing resources, and so all these kind of element node can be the judge of some outputs of the AI workload, so that they can monitor whether this output is aligned with human intention and value. And these element node can also work with each other in a decentralized way, so that based on their verification result, we can give the incentives accordingly from our system protocol. So we think that this is also a key part that can can help us to achieve the our vision, make AI public good.
Mm-hmm.
But that's the element node, and
So that's kind of still a work in progress.
still working in progress. Yeah, and next I want to try to introduce some of the application level platforms that we built, that we are building on top of our infrastructure. Is that okay? Okay. So the most important application we think on this AI infrastructure is the agent. So since we have the storage, we can store models, data here, and we have compute. Let's say we have some compute, and so when we build agent, we think an agent can really leverage our underlying system resources to make the agent more decentralized. And we think an agent in the decentralized world may have its unique values compared to the. I mean, each agent will have its own unique value compared to other agents. So it makes agent more like a NFT. So we want to map every agent to a NFT, so that the agent can first, it can have the ownership, and also it is unique to other agents, and thirdly, it can be traded and transferred in the decentralized platform. But in order to do that, so what we should put in this NFT for the agent? So we think the unique value of agent is it's a brain, it's intelligence. So what is the agent intelligence? It is the model and the data. And we think that the agent would be the very important applications on top of our decentralized AI infrastructure. So when we build the agent, and we think the agent should be agent in the decentralized world should be each agent in the decentralized world should be unique to the other agents, and we think the key unique thing of the agent is its intelligence, which include its model and also its context, the prompt, and also the memory kind of stuff. And this intelligence information can be stored in our zero-G storage network. And so in that sense, we want to map the agent to the NFT, because the NFT will give the agent the ownership. Yeah, and also can enable agents to be traded and transferred. So in this NFT, in the NFT, it actually describes who owns the agent, and also where the intelligence of the agent information can be accessed, which would be the URL link of the model and the memory of the agent. Then when the agent start to run, it will first be given a token ID, the NFT token ID. So the agent knows how to fetch the intelligence information from the NFT smart contract. And then the agent will use a compute resources from our compute network and ask the and run its body in this compute service, and then it loads the models from the storage to the system. As I described before, because this service network, this compute network can also support the fine-tuning service, so the agent can also training its model by using the input data from some users who is interacting with the agent, and so that the agent intelligence can even grow and evolve in the entire system. And but because the value of the agent intelligence, so that because the intelligence of agent should have value, and so that this information should be private, it cannot be easily copied to other agent. So when we do this agent transfer with this private model information, it cannot be supported by the traditional NFT standard, ERC, for example, the ERC 721. And so therefore, we actually invent a new ERC standard. We call it ERC 7857. And we also call it INFT, Intelligent NFT. So that we design a protocol that allows the users to transfer the agent with the private model data embedded in the NFT. The protocol is kind of there could be some subtle details there, and so high level speaking, we actually need to guarantee the atomic operation of the three things. One is the ownership change. Of the IMFT token, the agent, and the second is the the payment. Okay, the second is the payment of the NFT from the buyer, and the third one is the um, accessibility of the transferred model data from the seller. So yeah, so basically the transferring protocol need to make these three things happen automatically, and this is why the trickiness introduced. So also this is the reason that we will introduce this new ERC standard. And so based on this NFT based agent, and we actually built a agent platform which we call the AI verse, which is a platform to allow users to create and display on its own agent in the NFT form, and the agent may have the different utilities, and the users can train their agent in their specific way, and the AIverse also has a marketplace like similar to the OpenSea for the NFT, which allows users to buy and sell their NFTs to other users, and yeah, so this is a very new product that we are building, and yeah, it actually will be launched on Zero G mainnet very soon.
So if you own the NFT, you're the only one that can use it.
Yes, of course, yeah, and you can also define how other users can use your agent, and yeah, and also decide how you want
So they could charge, yeah. Cool. Is there anything else you want to cover, or should we wrap up?
Yeah, I think we can wrap up. Yeah, I think I've talked about a lot of things. Yeah.
Yeah, definitely a really good overview of what you guys are working on and what you have built. So, do you have any kind of future vision for zero gravity, or things that are coming out soon that you're really excited about outside of AI verse? And kind of like, where do you guys see yourself, in the next couple of years?
Yeah, definitely. So, in the future, so because our vision is very big, very ambitious, and in the entire system, we can see that there's a lot of challenges in the future. The efficiency, the scalability, and also the utility of the agents. Yeah, but this is on the developing side, and more generally, I think a purely decentralized AI system or AI environment is really good for the humans to achieve the holy grail of the AI of the like AGI, right? So basically, because I think for the AI model to achieve the human level intelligence, it really needs to get into a society environment that they can communicate and interact with the other agents and human beings. And in this environment, there should be some mechanisms to mechanisms to allow them to interact efficiently and with more purposes, and so that the AI agent can actually keep evolving and grow their intelligence. I think that's the very promising way to get us to this AGI future. And I'm very excited that Zero G is on this role, and yeah, and I'm really passionate on driving the zero G technical team to keep delivering new products to help us to achieve this vision. Yeah.
Right. Thank you so much.
Thank you. Thank you, Shane. Yeah.